or intramolecular forces. Okay guys, so in the previous slide we have pointed out about this gas particle has the attraction or repulsion, right? So there these type of forces, let's study on this topic. Okay, so if some system is there, they can have two type of the forces. If this is a molecule and because of some force atoms come together, held together, right, and a molecule forms. Let's say for example you have water molecule. For example, this is oxygen, hydrogen and hydrogen, right? Let's say in that what is happening, hydrogen attract to oxygen, oxygen attract to hydrogen. That's why they all are together, right? Hydrogen, oxygen and hydrogen, these all are together. They go everywhere where this whole as a whole water molecule go anywhere, so they don't separate each other. So there is one force, right? Force between atoms, and those force between atoms and provides you the molecule. That is one kind of force. But if you think about a glass of water, there are millions, billions, zillions of the water molecule, right? They all also sit together. This every molecule also are almost, they are also together, right? So there are two types of the forces. If you have a glass of water, so this is one water molecule. Now let me write that way. Okay, so this is one water molecule and this is other water molecule, right? So if you think about the what kind of the forces on this glass, there are two types of forces. You will see that one is the force that makes the water molecule, these atoms, the force which held these atoms together, that is one. Other is the force between this molecule and molecule, force between these two water molecules, right? So force between two particles, two water molecules, that is one kind of force. Other is the force between the atom that makes the molecule, that is other kind of force. Let's study about these forces. Okay, so one of the forces is said to be the intramolecular, other is the intermolecular. Intramolecular force makes the molecule done, but the shape and the phases of the particle, phases of the materials is made by intermolecular forces. So water is water molecule because of the intramolecular forces or force between the atoms, but the water is the liquid because of the intermolecular forces. So that's why intramolecular, within the molecule, the force within the molecule, intermolecular, force between the molecule, and these forces arise due to attraction between partial charges or between ion and the molecules. These forces determine the physical property of the substance. So the intramolecular force means force between two molecules determines what is the phase, whether it is solid, liquid or gas. What is the property, physical property, right? Physical property of the material is determined by the intermolecular force. Something is liquid because of the intermolecular force, the attraction between the two molecules. That the liquid is because of the attraction between two molecules. Something is solid because of the attraction between two molecules. So these forces, these intermolecular forces, are the force between the molecule, and they are generally the attractional force, and these attractional force are because of one is the partial charging. So for example, if you think about the water, so hydrogen has positive partial charge, this has also positive partial, means not full charge, these are some fraction of the charge, partial charge, and oxygen has negative. So look at that, they are very weak positive and negative. They are partial charges, weak positive and negative. They are not full charge, means they're not -1 or not +1, but they can be plus 0.5 or plus 2.5 or minus 9.5, like minus 0.5, like that. They are partial charges. So these intermolecular forces, the force between molecules, are because of these partial charges. One reason is that. Other is, and the other is, or between, if they are ion also. One is positive ion, one is negative ion. For example, sodium chloride. Sodium is positive, chlorine is negative, there is another chlorine, another sodium, right? So this is attraction between ions, or attraction between molecule itself also. They don't have positive, they don't have negative, but attraction between simply the molecules also, because of the mass, because of the momentary, very short periods, positive and negative. So sometimes what is happening is electrons are moving, right? So because of the motion of the electron, sometimes more electron accumulates to one region, less accumulate to other region for a very small time. So let's say, for example, the water. This is the water. So what happens is electrons are moving. What happens sometimes more negative here and less negative here, more positive here, less positive here. That happens. So but for very small time, very small, tiny amount of time, electron can have more electron energy can be in one side of the molecule, less energy can be other side of the molecule. Because of that movement, that very small intervals at charge accumulation, you may have attraction between positive and negative. So a good example is for example, let me take the very good example of the this kind of these three. Okay, so one attraction between partial charges. One water is here, so let me see that. So okay, let me draw in here. Okay. So this may be easy. So let's say this is water molecule. Okay, water. So what happens is, because oxygen is more electronegative, so oxygen pulls the electron energy toward itself, and what is happening is, whatever the electron cloud is, this is suppose the hydrogen's electron cloud, this is suppose other hydrogen's electron cloud, this is suppose oxygen's electron cloud. Okay, what happens is oxygen is more electronegative. That's why what this oxygen does is, let's say this is hydrogen, this electron cloud, this guy pulls toward this, and what is happening is, this has tiny electron cloud left behind, but more electron cloud will be accumulated here. So, more electron energy, very small tiny amount left there. For example, 75% of electronic energy this oxygen pulls toward itself. 75% of this pulls toward. So this has this much negative charge, but this has this much electron energy. So this eventually turns, this is a partial negative, and this is losing electronic energy, right? It's electronic energy more pulled by other. That's why it's losing some portion of the electron energy. That's why this becomes positively charged, and it also loses. Let's say this is only that much left behind, right? That much left behind. All others say this pulled by that. So that's why it is losing some electron energy. That's why it is delta positive. So this kind of scenario happens in certain molecules, not all molecules. Certain polar molecules, this kinds happen. If you have the more electronegative atom and less electronegative atoms held together, then this kind of scenario happens. For example, the water. Hydrogen is less electronegative, oxygen is way more electronegative than hydrogen. That's why more electronegative oxygen pulls the electronic energy toward itself. So this scenario happens. So if that happens, what happens is, oxygen and the hydrogen. This is one water molecule. So you have another water molecule also in your glass of water. There are lots of water molecules. Then what is happening is, this is delta positive, this is delta positive, this is delta negative. So what is happening is, now let me draw another way. Okay, this what is happening is, let's see that easily. I will plot. Okay, now hydrogen, oxygen, delta minus, delta plus, hydrogen. So this is hydrogen delta plus. This is hydrogen delta plus of another water molecule. Then its delta plus. Positive always attract negative, right? Oxygen's delta plus is this. Oxygen's partial charge, hydrogen's partial charge. There is the attraction here. So here is also. This is positively charged. Oxygen is negatively charged. So they also will attract. Okay. So then this oxygen also can attract this guy. This oxygen also can attract this guy. So there is a very case, right? Loss of attractional forces. Because of these loss of attractional forces, they held together. That's why water molecule always together. There you have a water. However, this is the liquid, but you have water as a substance. If there is no attraction, they all will fly away and you don't have any substance. So this scenario is one happens. Other scenario happens is, let me give you sodium chloride. Let's say sodium plus chlorine minus, right? If they are in water, they attract together. So there is attractional force between this full positive one charge and full negative one charge. That's another thing happens. So other thing happens is, for example, let's say methane molecule or propane molecule. Let's say propanol. Let's say carbon, 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 OH. This is propanol. Okay. So hydrogen. This is propanol. Okay. What happens is electrons are moving here, 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 everywhere electrons are moving, right? But some very small time, what happens is electron accumulates here. For very small time. So this has less electron energy, this has more electron energy, but this is not like that. This scenario is forever because electronegative atom is this that pulls and keeps it with itself. But in this case, that don't happen. Both are electropositive. That's why what happens is it pulls the electron. It is positive, it is negative, but that is for a very small interval of time. And in that very small interval of time, you have attraction. So if you have another propanol, right? So if you have another propanol, it's here. If you have another propanol, there is attraction, overall attraction between this guy and this guy. So that is not like this attraction, because this scenario is the permanent. Because oxygen is electronegative, it always pulls electron with itself and keep itself. But this is not permanent, very temporary, very small moment of time. So there is also attraction, but this is very weak attraction. So this is another type of attraction. That's why basically you have three types of attraction. So what can happen also, it is, let's say sodium chloride is here. If you have water is here, say water has delta positive, delta negative, delta positive, right? This is full positive and this is negative, right? However, it is delta negative, but this is positive and this is negative. That's why there is also attraction. So ion-dipole, this is said to be the dipole, ion-dipole attraction. This is said to be the dipole-dipole attraction. This is ion-dipole attraction. This is molecule-molecule attraction, or this is also said to be the momentary dipole attraction. Very small moment. There is also, for every molecule has momentary dipole present there, whether it is electronegative or electropositive. For very small interval of time, every molecule gets the dipoles, but that dipole is very, very weak dipole, So however, this is also dipole-dipole interaction, but that is weak, momentary dipole interaction. This is another type of. So that's why if you think about the attraction, the force between the molecule or intramolecular force, we have basically four types. One is the dipole-dipole, other is the ion-dipole, one is the ion-dipole, dipole-dipole, other is the momentary dipole and the momentary dipole, and the charge or ion, sodium and chloride. And Okay, they are basically the full ions, right? So that's why they have attraction. So basically you have 4 types of the attraction. So you have basically 4 types of the intramolecular forces. Now let's go study them. So this, okay. So there are 4 types of the interactions. So you have 4 types of the forces, and they are said to be, some are said to be the van der Waals force, some are said to be the hydrogen bondings, some are said to be the ion dipoles, like that. So these were the van der Waals distance. Now let's think about the van der Waals distance. So can they attract for anywhere? So one molecule is here, other molecule is there. What is the distance? So there is certain distance, that is the van der Waals distance, is the distance between 2 non-bonded atoms in adjacent molecules. So this van der Waals distance is the distance between the non-bonded atoms, basically where they can attract. For example, if you have this water molecule, this is one water molecule, this is another water molecule, right? So what is the distance between these two molecules, non-bonded atoms? For example, van der Waals distance between these two, this is the van der Waals distance, right? Because they are not bonding. This oxygen and this oxygen, these distances are the van der Waals distances. Okay, so non-bonded atoms of 2. The van der Waals radii is the 1/2 of the closest distance between the nuclei of 2 non-bonded atoms. So if 2 atoms are not bonded, for example, now let me erase all of them. So this is one water molecule. Okay, let's say this is oxygen, and this is the hydrogen. But these hydrogen oxygens are bonded together. Let me take another water molecule also. This is, right? See, this hydrogen and this hydrogen is non-bonded. They are non-bonded atoms. This hydrogen and this oxygen also non-bonded atoms. So what is the van der Waals radii? Is the 1/2 the closest distance between the nuclei of 2 non-bonded atoms. Closest between. Now if you see that here, let's see that these two are bonded, right? That's why distance between this guy and this guy is the bond length. This is the sphere, right? Its radius plus its radius is the bond length. Bond length is equals to radius of one atom plus radius of other atom. That is the bond length. Okay, that's the bond length. So, but what is the van der Waals distance between the 1/2 of the distance between 2 non-bonded atoms? So let's see that this atom and this atom, this is the distance between these two, and 1/2 of the distance between these, because they all atoms are similar in size in this model, that's why the 1/2 of the distance between these two, that's the van der Waals radius. So in this case, let's see that here, this is the distance between 2 non-bonded atoms. That's why it's so it's a 1/2 of that, 1/2 of the closest distance is the van der Waals radius. This is the van der Waals distance, right? Distance can be any. So some particles are farther away. Now let's go to the other drawing. Now let's see here. So let's say this is one atom of molecule, this is another atom of molecule, right? So this is the center, this is another center. So this is the radius of one atom, this is the radius of other atom. So this total distance between these two radii, the center between one atom and other, is this is the bond length. These two are molecule held together. Okay, let me try to make a little bit better one, and say this is another. Okay guys, so these two atoms now. Yeah, look, that's good. So, okay, now let's say you have another molecule is here, but let me make these two little bit bigger. Okay. See, okay, now let me change the color of these also so that they looks good. Red outline, also red. Now, nice. We have, if you see that, we have two types of the atoms here. This is one molecule, molecule 1. This is molecule 1. This is molecule 2. So intramolecular forces means that the force between this blue molecule and red molecule, right? So bond length is, now its center is this and its center is this, right? This is the radius, and if you connect two centers, that is the bond length. This, the distance between center of two atoms is the bond length. Distance between center of two atoms of the same molecule, bonded molecules. But look at that, this is molecule A, this is the atom A, this is atom B, and let's say this is atom C and atom D, right? A and B are bonded together, but A and C are not bonded together, right? So distance between center of two bonded atoms is the bond length. But let's say other distances also. Now let's see that, okay, let me make little bit like this, okay guys. Now it is easy to understand now, okay. So D, okay. Now if you, it's the center, this is the bond length of the CD molecule. Molecule 2 bond length is equals to CD, bond length of molecule 2. Bond length of molecule 1 is AB, union the bond length. Now let's see that distance between center of these two. This is also one distance, right? Now let me take another color, basically this one. Okay, let's see. This is the distance between center of these two atoms, and let's say this is the distance between center of those two atoms. Now let me even make a little bit farther, okay guys, for your easiness. So CD, okay, this distance is bond length, but let's see that this distance, BD distance, is one distance, and AC distance is the another distance. So distance between these two non-bonded atoms, AC and BD, is van der Waals VDW distance. This is the van der Waals distance. So BD is smaller than AC, right? There are two van der Waals distances, AC, but the smallest distance is BD, right? BD is smallest distances, smallest van der Waals distance. So BD is said to be, BD is called van der Waals radii, van der Waals radius. So van der Waals radius means the half of the, so let's say BD is the van der Waals diameter, but the van der Waals radius is half of that. Let's say this half of BM. So BM is equals to half of BD, and this half of BD is said to be the van der Waals radius. So van der Waals radius is equals to half of the minimum distance between two non-bonded atoms. That is said to be the van der Waals radius. So now let's go further. So like covalent radii, if you see that the trend of the covalent radii, let's see that. Okay, so blue circle is the covalent radii and red circle is the van der Waals. Blue covalent radii means radius, the distance between two bonded atoms. Covalent bond, right? If it makes the bond, what is the trend in the covalent bond or the bond length? Look at that. It decreases horizontally, it increases vertically in the periodic table. Bond length, so we have two things, right? If you see that, we have two things here. One is the bond length. This is the bond length. CD is also bond length, right? CD, right? The CD is bond length, right? So what happens to the bond length? Bond length increases horizontally. The covalent bond. If something has the covalent bond, covalent radii, then that increases horizontally. Similarly, the van der Waals radii also increases the same pattern. Van der Waals radii also has the same pattern. Okay, so the van der Waals radii decreases across the period and increases down in the group. This is very important information. We have to remember that. So covalent radii also increases also decreases horizontally and increases vertically in the periodic table. And similarly, the van der Waals radii also increases increases vertically and decreases horizontally in the periodic table. So the van der Waals radii is one half of the closest distance between the nuclei of non-bonded atoms, and it increases vertically in the periodic table and decreases horizontally in the periodic table for 14, 15, 16, 17, these one. Okay, and then it is always larger than the covalent radius. Always larger than the covalent radius. Okay, guys. Now let's see why that is. See, covalent radius is, now this can give you covalent radius, right? Up to here to here, it gives you covalent radius. But let's see that van der Waals radius should be between two molecules, right? See, this is, if you think about BL, let's say BL is covalent radius, but BM is van der Waals radius. So van der Waals radius, that's why always smaller than covalent radius, right? Covalent radius is equal to actually radius of the atom. That's the covalent radius. But the van der Waals radius is outside, always outside of the atom, because it is the sum of the radius distance between two molecules, and two molecules never come together. If they come together, that's the covalent. And the non-bonded, if they bonded together, that's the covalent. Non-bonded together means they are always farther away. That's why this is the van der Waals radii is always larger than the covalent radii. So now let's go further. So comparison, if you compare that, the energy also, right? Ionic bond, you have this much energy, 400 to 4000. Covalent force, you have 150 to 1100. But the metallic, you have 75 to 1000. These are some example. Okay, so that's why ionic is the strongest force, ionic. Now comparison of the non-bonding forces, we already discussed it, right? What are four types? So ion-dipole. So basis of attraction is ionic charge and dipole of charge. Energy is 440 to 600. Hydrogen bond 10 to 40. So what is the hydrogen bond? We will study in a minute. So hydrogen bond means a bond formed between the hydrogen and the other nitrogen, oxygen or fluorine. So we will study that right now. There is a hydrogen bond also. Its energy is 10 to 40. Dipole 5 to 25. And the van der Waals force, this is 0.5 to 40, right? See, all of them are less in energy, less powerful than the bonded force. Now you see that ionic, covalent, metallic, they have 400 to 4000, like that. They all are very strong. But the non-bonded forces, these are the non-bonded. Okay, guys. these are the intermolecular forces, are weaker than the intramolecular forces. So bonded forces has 400 to 4000, but the non-bonded has just 0.5 to 600. That's why they are weak. Okay, they are weak. So we have an ion dipole, hydrogen bond, dipole-dipole, and dispersion. That is all the van der Waals force. So these four types of the forces. Now let's see here what are they. Okay. However, we have already studied four types of the interaction. Okay. So we have four types of the interaction. So now let me show you like this. Okay. So ion dipole. So ion dipole is, if you see that, one is the ion and other is the dipole, right? Ion is positive, you know ion is positive. Dipole means it has two poles. So like for example, water, right? Oxygen, hydrogen, hydrogen, right? Oxygen pulls lots of electronic energy toward itself and it is a partially negative, right? So what happens is it has two poles, right? Negative here and positive here. This is the negative pole, this is positive pole. So it has two poles, right? So the attraction between these two, that is the ion dipole, and its energy is about 40 to 600. This is strongest. Ion dipole is strongest. So other is the hydrogen bond. Hydrogen bond. Hydrogen bond is the bond formed by the partial charge between the dipole. Okay, it is also due to the dipole-dipole, but the stronger dipole-dipole. Okay, polar H bond, H dipole charge, high electronegativity of nitrogen, oxygen, and fluorine. So what happens is the bond, that the attraction between dipole due to nitrogen, oxygen, fluorine, and the hydrogen, or bond between electronegative nitrogen, oxygen, fluorine, and hydrogen attached with these due to dipole, and that bond is said to be the hydrogen bond. What happens is, if the hydrogen, now let me write down that better way. Okay, so there is another kind of bond. Okay, not the covalent bond. This is neither ionic bond nor covalent bond. The hydrogen bond is the bond between hydrogen and either nitrogen or oxygen or fluorine. Okay, the bond between hydrogen or nitrogen, or hydrogen and fluorine, or hydrogen and the oxygen. So but this is not the covalent one. So hydrogen of other molecule and oxygen of other molecule. Hydrogen of separate molecule and oxygen of separate molecule, not within the same molecule. Okay, so if you have a hydrogen, is hydrogen of the another molecule and oxygen of another molecule, and that hydrogen is also attached with either nitrogen, oxygen, and fluorine. For example, let's say water, you have one hydrogen, other hydrogen. Let's say hydrogen attached with oxygen, right? Oh, nitrogen, oxygen, fluorine. Yes, any one of them, hydrogen attached with nitrogen, oxygen, fluorine, and you have either oxygen here or nitrogen and fluorine. For example, another water molecule. Let's say this is another water molecule. See, you have the oxygen here and hydrogen attached with the oxygen, but this hydrogen is with different molecule, right? This is the molecule 2 and this is molecule 1, and this attraction. So because it has a delta minus, it has delta positive, it has delta positive, it has delta negative, it has delta positive. That's why attraction between these two also forms the bond. This bond is the hydrogen bond. Okay, there could be another hydrogen bond. Let's say there could be another attraction, right? Hydrogen or oxygen of this molecule and hydrogen of this molecule. This is another hydrogen bond. There is another, this hydrogen and that oxygen. That is another hydrogen bond. So this hydrogen and that, this oxygen and that hydrogen, that is another hydrogen. So that's why the hydrogen attached with either nitrogen, fluorine, or attached with.
Okay. So let's repeat the hydrogen bond. Okay. So hydrogen bond is, for example, let's say other molecule CH3, CH2OH. Okay. So if you write this molecule a little bit open form, so CH, I would write that way, showing the bond also, CH, and ONH. See, this hydrogen is attached with the oxygen, right? So if you have the similar other molecule also, let's say other molecule also, for example, water, so oxygen, hydrogen, and hydrogen, right? So this hydrogen is, if you see this hydrogen, this one, this hydrogen is the hydrogen attached with the oxygen, but this is of the different molecule. And this hydrogen also, the second hydrogen also, let's say this hydrogen number 1, hydrogen number 2, this is hydrogen number 3. So hydrogen number 3 also attached with oxygen, hydrogen number 1 attached with oxygen, right? It fulfills the criteria, right? Oxygen, hydrogen attached with oxygen, but the different molecule. This is this hydrogen of the water and this hydrogen of the ethanol, right? So in this situation, there may be the hydrogen bond between this oxygen and this hydrogen and this oxygen, this oxygen and this hydrogen, right? So these type of bond are the hydrogen bond. That's why, so hydrogen bond is the bond between hydrogen attached with either nitrogen or oxygen or fluorine, and either nitrogen or oxygen or fluorine of different molecule, or if this different molecule or different group or different location or group. So this is the hydrogen bond. So to be the hydrogen bond, it's not necessary these should be in the same molecule, but they could be non-bonded, but that's it. The main thing is the non-bonded. So this hydrogen bonded with the nitrogen, but this other nitrogen should be non-bonded nitrogen. That could be in the same molecule or that could be in the different molecule. So let us correct this, okay, the definition. We can give the different example also. This is, see that in this scenario, this hydrogen is not the bonded hydrogen with other molecules. So non-bonded hydrogen and non-bonded nitrogen, right? That could be in the same molecule also. Now let's see one example. I can show you one example, okay? So let's see one example. Let me erase this and have the different example. Now let's see that. So let's see, this is the molecule CH, CS3, C, N, H, 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 H. See, this is the nitrogen, right? See that? This is the nitrogen here. This hydrogen attached with nitrogen. Good. This is fine. But now let me change the formula of this this molecule. So let's see that here. There is another carbon here, and this carbon has hydrogen, and this carbon has oxygen, and hydrogen, and hydrogen. See, this is the molecule. Okay, look at that. This hydrogen connected with the oxygen, this hydrogen connected with the nitrogen. Those both hydrogen can make the hydrogen bond, and this hydrogen can also make the hydrogen bond, right? Because this is connected to the oxygen, this is connected to the nitrogen. So suppose that there is one water molecule here, one water is here, oxygen and hydrogen. Let's see, this is delta positive, this is delta negative, this is delta positive dipole here, right? Here is also the same thing. This is delta positive, this is delta negative, this is delta positive. Similarly here, delta positive, delta negative, right? So there are many chances for making the hydrogen bond. So this can make the hydrogen bond here. Okay, so that can make the hydrogen bond. So similarly, this one can make the hydrogen bond here, right? This hydrogen attached with oxygen and nitrogen is in a different place. Non-bonded nitrogen, right? This is not bonded with this hydrogen. So this oxygen can bond with this hydrogen. This hydrogen also can have hydrogen bond with this oxygen. This hydrogen can also bond with this oxygen. This hydrogen also can bond. Look at that. This. How many hydrogen bonds? Look at that. This hydrogen can. Okay, let me change the color to make it a little bit different. Okay, so now let's see. This hydrogen can bond it. Already we have give that, right? This hydrogen can bond with this oxygen. This hydrogen also can have the possibility. This hydrogen can also have the possibility with this bond. You see that this is the hydrogen bond network. This is said to be the hydrogen bond network, right? This oxygen can bond with this, bond with this, bond with this, bond with this. This nitrogen can bond with this hydrogen, that hydrogen. Okay, this nitrogen also can bond with this hydrogen. See? So that's why there are many chances. These are the hydrogen bond network. So that's why we can define that hydrogen and either nitrogen or oxygen or fluorine, but these should be of the separate molecule or separate group within molecule. So same molecule also, look at that, this is the same molecule, right? This molecule is same molecule, but it's making the hydrogen bond. Look at this oxygen making with this nitrogen making with this is making the hydrogen bonds, right? That's why hydrogen bond can be between two different molecule or between two different group also. This is the hydrogen bond. So this is the hydrogen bond, and we will discuss another types of the intermolecular forces in the next video. And right now, up to this, we should learn up to the hydrogen bond, and the next video will discuss about the another type of the bonds. Okay, so see you for next video.